Hello, welcome to Lesson 8, some application problems. This first problem is called the birthday problem. The statement is, in a room of n people, what's the probability that at least two people will have the same birthday? In this context, we're talking about month and day and not year. We're going to be ignoring the leap day in this solution, and we will also make an assumption that the probability of being born on any one of the 365 days is the same. It's all 1 out of 365. Again, in reality, it's not quite that perfect, but it's close enough that this will give us a very good, very accurate answer here. So again, the question is, in a room of n people, what's the probability that at least two people will have a matching birthday? Suppose we have two people. What's the probability they have the same birthday? So in this situation here, the first person's birthday doesn't really matter. What matters is that the second person has to match the first. So the first person could be born on any day of the year, 365 out of 365, and then the second person has to match the first person. And there's only one birthday that they can, there's only one day that is a correct match. So it's 1 out of 365. So when there's two people, the probability of a match is 1 out of 365. Now, what happens if we change this to 3? Well, there's going to be more possibilities because the question is at least two people have the same birthday. So we have a lot of possibilities here. A and B, if we call the people A, B, C, A and B could have the same birthday, A and C, B and C, or all three. So we see here that the number of different cases here jumps up. And if you extend this out to much larger numbers of n, it's going to be pretty difficult to keep track of all that. So we're going to look at the opposite point of view. The opposite point of view of at least two people having a match, at least two people having the same birthday, the complementary situation is that everyone has a different birthday, that there are no matches. So this is the complement. The complement of at least two people having the same birthday is that everyone has a different birthday. So we're going to calculate that instead. That's going to be easier to set up, and then we're going to subtract from 1. So what's the probability that the three people all have a different birthday? Well, again, the first person doesn't matter, 365 out of 365. The second person has to avoid matching with the first person. So there's 364 ways to do that out of 365. The third person must avoid the first two. So there's 363 out of 365. Now we want the complement of this. So we want 1 minus this probability, which we can rewrite here in the form 1 minus 365 permutation n over 365 to the nth power, where n is the number of people. Okay, so for n equals 3 here, we have 365 P3 upstairs. Downstairs, we have 365 cubed. So 1 minus this is about 0.0082. So it's a low probability here when n is 3. It's a low chance, less than 1% chance that there's at least one match. Now in this course here, we have approximately 30 students. And this answer may be a little surprising here for what the probability is when we have a group of 30. So the probability of at least one match is 1 minus, everyone has a different birthday, which is 365 P30, divided by 365 to the 30th power. and it comes out to about 0.7063. So about 71% chance. So a little bit maybe counterintuitive. With 365 days, it does turn out that you have 30 people. The chances of at least one matching birthday is over 70%. And the probability reaches above 50% at n equals 23 people. Now, in order to guarantee a match, we would need to have more people than possible days, which would be 366 or 367 if you count the leap day. That would guarantee it. But we don't have to go that high up to get a very, very high probability. We have a graph here, and we see that when we reach 23, the probability goes above 50%. At 30, we had it a little over 70%. We're up to, at 50, we're, over 90% at that point. Okay, up next, a couple of Bayes' theorem examples. So recall Bayes' theorem, conditional probability A given B. It's a reversal, probability of B given A times probability of A. And then the denominator, we have to basically work through the cases. Now, in this particular situation, we have just A and A complement, but it is possible that there may be more than two terms in the denominator there. But it's probability B given A times probability of A, matching the numerator, plus probability B given A complement times probability of A complement. All right, so in this question here, we have three urns. The first one contains 3 yellow, 2 green marbles. The second, 4 yellow, 1 green. The third, 2 yellow, and 5 green. We're told that a marble was selected and it was green, and we want to find the probability it came from urn 3. So we want the probability that urn 3 was used given that a selection was green. And so using Bayes' theorem is going to be helpful because turning that around to the probability of a green given that urn 3 was used is a lot easier to calculate. If we know we're in urn 3, we can figure out the probability of green. It's 5 ways to get a green out of a total of 7. And we'll do similar calculations for urn 2 and urn 1. So a little bit of an extension here from the basic formula. We have 3 different urns here. We have 3 possibilities here for getting a green. So we have to include each case there urns 1, 2, and 3. So what are these new conditional probabilities in Bayes' theorem after reversing? Well, as mentioned, the probability of green given that urn 3 was used is 5 out of 7. For urn 2, it's going to be 1 out of 5. There's 1 green, 4 yellow for a total of 5. And in urn 1, it's 2 out of 5. So that's going to be used here in the conditional probabilities. Now, the probability of selecting any urn problem should have specified here, but we're going to assume that it was equally likely to pick any one of the urns. We're going to assume that that probability is that selecting a specific urn is 1 out of 3. So we're going to have a common 1/3 in every term. Now, in the numerator, it was the probability of green given urn 3 times probability of urn 3. So it's 5/7 times the third. 5/7 we got here. And then the denominator, we have that same term plus the conditional probability of green from urn 2, which was 1/5. Probability of selecting an urn is 1/3. And then we come to urn 1. Probability of green, given that we're in urn 1, was 2 out of 5. Probability of selecting urn 1 is 1/3. We cancel out the 1/3s, and we simplify this complex fraction. We get 25 over 46 6, which is about 0.543. So that's the probability that EARN3 was used, given we know that the selection came out a green. All right, another example here of Bayes' theorem. A blood test indicates the presence of a particular condition 95% of the time when the condition is present. So we're getting a positive test out 95% of the time when the condition is present. The same test indicates the presence of the condition 0.5% of the time when the condition is not actually present. 1% of the population actually has the condition. Calculate the probability that a person actually has the condition given that the test indicated the presence of the condition. Positive test. So let T indicate testing positive. The complement of that, T with a superscript C, is testing negative. Let D indicate having the condition. D complement not having the condition. So the 95% is a conditional probability. It's telling us that the probability of testing positive given the condition is present is 95% or 0.95. So that's the probability of testing positive given the condition is present, and that's 0.95. Now, the 0.5%, which in decimal form, going two places to the left, is 0.005, that was the probability of testing positive given that the condition is not present, which is D complement, and that's 0.005. There's a 1% chance of actually having the condition, so the probability of D is 0.01. We want to find the probability that a person has the condition given a positive test. So we're trying to find the probability of D given T. The probability a person has the condition, D, given that they tested positive, T. And so, once again, we see here that the reversed conditional probability was given in the problem. All right, so in this case here, we're just going to have two cases here, either either having the condition or not, D complement. So only two products in the denominator. So the probability of D given T is reversing probability T given D times the probability of D. Downstairs, we have that exact same term again, plus the probability of T given D complement times the probability of D complement. And we're going to fill these things in here. So one calculation we need to make is the probability of D complement. That's 1 minus the probability of D. So the probability of D complement is equal to 1 minus 0.01, which is 0.99. All right, so let's piece it together here. Probability of T given D was 0.95. The probability of D having the condition was 0.01. Downstairs, we have the same term again, 0.95 times 0.01, plus the probability of T given D complement, which was 0.005, times the probability of D complement, which we calculated to be 0.99. And simplifying this, we get 0.6574, which is the probability of having the condition given a positive test. So in percentage form, it's 65.74%. All right, this concludes lesson 8. As always, please don't hesitate to email if you have any questions. Thank you.